If you want to understand how machine learning really works under the hood, matrix multiplication is one of the most important concepts to learn. In this video, we'll cover the types and rules of matrix multiplication, its applications, parallelization techniques, and its role in machine learning. Before we get into matrix multiplication, you might want to check out the video, What are Matrices? It'll give you a solid foundation. Other types of matrix multiplication exist, but they are not part of this lesson. These include element-wise multiplication, matrix vector multiplication, dot products between vectors, scalar multiplication, and more advanced operations like Kronecker products or tensor multiplications. However, we won't go into those here. Our goal today is simply to understand one type of matrix multiplication, the standard row by column multiplication you learn in algebra. First, we'll explore the fundamental rules that guide how matrix multiplication works. In standard matrix multiplication, also called row by column multiplication, each element of the row vector is multiplied with the corresponding element in the column vector. Then summing the products will give you the value in the first row and first column in the resulting matrix. Next, we multiply the first row of the first matrix and the second column of the second matrix. This process is then repeated with the rest of the columns of the second matrix. After the first row has been calculated, we continue the same process, but for the second row of the first matrix to get the resulting matrix's second row. And we repeat the process for each row for the final result. Let's look at some use cases for matrices. Let's say you have 3 different construction methods for building a box. Each method uses a different number of materials, and each material has a cost depending on where it is shipped from. Let's use matrix multiplication to find the most cost-efficient method to build our box. This matrix shows that producing 1 unit of A requires 5 pieces of wood and 2 pieces of metal. Producing 1 unit of B requires 3 pieces of wood and 4 pieces of metal. Producing 1 unit of C requires 6 pieces of wood and 1 piece of metal. The second matrix shows us the price of wood in the US is $10 a unit, and in Canada it's $12 a unit. The price of metal in the US is $20, and in Canada it's $18 a unit. When we apply the rules we learned in the previous slide, we find out that it costs $90 to produce A in the US and $96 to produce A in Canada, $110 to produce B in the US, and $108 in Canada, and so on. As you can see, producing unit C in the US is the most cost-efficient method. Matrix multiplication isn't some concept to forget after an exam. It provides a unified way to solve real-world, multivariable problems like material costs, recipe scaling, and budgeting. While these small examples could be solved with basic arithmetic, many modern applications involve datasets with millions of rows and columns. At this scale, solving problems by hand or with a simple calculator becomes impossible. This is why fields like machine learning, computer graphics and image transformations, and network analysis rely heavily on matrix operations and cutting-edge technology to solve complex data-driven problems. Speaking of computers and machine learning, graphics processing units, GPUs, are extremely efficient for matrix operations. Each multiplication and addition can be done separately by different parts of the GPU, allowing multiple calculations to run at the same time. Modern GPUs use advanced techniques like pipeline scheduling to further optimize and speed up matrix multiplication by efficiently scheduling operations and minimizing idle time. These behind-the-scenes mechanisms greatly improve efficiency of such operations, but their detailed inner workings are beyond the scope of this video. Before we recap and end the video, here are some brain teasers for you. Assuming there is no pipeline scheduling, how many GPUs are necessary to run all operations in the matrix above in full parallel? And assuming that the machine has only 6 GPUs and no pipeline scheduling is used, how many parallel transactions will it take to complete the entire operation? We would love to hear your answers, so leave your questions and comments below. And don't forget to subscribe and visit our channel for more videos. It helps us create more content. Let's recap. In this video, we covered matrix multiplication and the rules for how it works. Then we explored some of its key applications. We also talked about how multiplication operations can be parallelized to run faster. And finally, we touched briefly on how matrix multiplication is used in machine learning. We also recommend the following videos to help you build a solid understanding of the machine learning topics we will cover in the future.